Okay, so we're going through the elevator pitches in the order of the talks. And so let's start with Sure.
Oh, I think there's just one slide.
Yeah, that's just a slide for you. You just say what you want to say. What's your research about?
Hi everyone, I'm Joel from the University of Melbourne. So, what's your favorite programming language? Well, whatever that is. I'm sorry. My one's Haskell. So, as a functional programming language, Haskell has an advantage of being mathematical, high level, and abstract, which makes it really nice tool for proving things like program's correctness against its specification. And so, for this reason, we are interested in functional programming languages. And when we use them, we want to know how long and how much time and how much space it will take for that program to give us the output we needed. So in that way, we need an algorithm, which is a cost model, to give us the cost for our program. And so for different functional programming languages, they're based on number calculus, which have different evaluation strategies. So for different languages, essentially with different evaluation strategies, we need very different cost models for them. And which means we actually need to develop different cost models from scratch because their properties are different. And is there a way to solve them once and for all? So instead of making one from scratch every time, can we just make one thing that works for everything? And that's when my call by push value comes out. So call by push value is a number calculus that's able to allow user to define when and where to actually evaluate their computations. So if I can give a cost model for call by push value, I can then extend it easily for call by name and call by value, things like that. So if you want more details about verified cost model for call by push value, that will be my talk at 10:30. First one up as well. Thank you.
Hi, my name is Naya. My research is about complexity analysis and trying to apply it in practice. I have this hypothesis that if we take implicit computational complexity, this is called ICC, then we can get some new automatic approaches to doing complexity analysis and also able to resolve some limitations that exist in current methods. This is not necessarily obvious because ICC is a very theoretical approach and it hasn't been applied much. So in my research, my objective is to work on this hypothesis in 3 different ways. First is to say that we can actually apply ICC in practice. That's actually a doable goal. The second thing is that I want to formally verify an ICC method to show that we can get formally verified complexity. And then there's a third application, which is this kind of extended use where we can put ICC in, use it during compilation and optimize complexity properties. I think the formal verification aspect is super interesting because the certifying complexity analysis technique hasn't been done before. And then taking all that combined, then there's this idea that ICC is not just for theorists, but it can move forward this kind of practical analysis.
Thank you.
So in the next session, I will talk about this proven omniverse of probabilistic algorithm with formal verification. So we say the omniverse needs is a security definition, which will defending against the side channel attack between the memory and the CPU. And there is a deterministic version, which is the original version. And there is a probabilistic version of the definition of omniverse. But the probabilistic version is a little bit harder to reason about, and there is only few works of the formal verification logics will try to do this work, and I will try to extend existing work called PSL, which is probabilistic separation logics, to try to extend that to reason about verifying the omniverse, which is a probabilistic version, and I will talk about that.
I'm sorry for misspelling your name there.
Good morning, everyone. So my name is Sumit. I'm from IIT Kanpur. So the things that I mostly work on are verification of programs with concealed components. Well, what the problem is that symbolic or regular verification requires logical encoding of the program, along with that some logical specifications. So the whole thing has to be in a way be formally specified for the approvers or SMTs to work properly. However, real-world programs contain lots of components whose common semantics are not known. This could be some like functions from external libraries, or it could be some cloud-based APIs, things like that. So, how do we still write verification for programs where such concealed components are present? So, what we employ is a technique known as almost verification, which is kind of a software testing-based technique. We still try to verify over such programs which contain concealed components. And in my talk, I'll talk about like how I have applied almost verification for different kinds of oracles or programs.
Good morning, everyone. My name is Sanjeev, and I'm a PhD student at IIT Kanpur. So my work is focused on designing scalable solutions for complex systems, such systems where you may have components that are hard to model. So in such scenarios, how do you sort of validate the safety or security of the systems? So formal techniques are very not that easy to apply in such cases and may involve manual efforts. But however, testing-based techniques such as fuzz testing are relatively easy to apply and they are fully automated. So in my work, I try to sort of assist formal techniques using fuzz techniques. So just to have a system that can scale for large systems and the system which may contain components that are hard to model. Yeah.
Quite a long title. So hi, I'm Julian from TU Darmstadt, and I'm interested in distributed and collaborative software. And if we think about this type of software, typically it's cloud-based nowadays. So if you think of software like Google Docs, everything happens pretty much in the cloud. And if you ask me, this has several important downsides. The most obvious one probably being offline availability. We can't really use these applications when we're offline, when we're not connected to the cloud. But probably more importantly, we also use a lot of data ownership and privacy properties that we might like. So we suddenly can't really control where our data lies. And for most users, the cloud really functions as a black box. They don't really know where their data is stored, where these servers stand, and they also don't know where their data is processed and how it is processed. They also can't take the data and use it with another service. And if the cloud provider suddenly decides to stop the cloud service, users are simply forced to accept that decision. Now, local first software is kind of a different approach to these distributed software. And the idea here is that every user keeps a local copy of the data on their own device, and they get to decide whom they want to collaborate with and whom they want to send their data to. So it's more like a Git approach where everyone has their own local copy, and then there's some way to merge changes from others you want to collaborate with into your own copy. Now, this type of software is kind of hard to reason about, especially if we want to verify it. And this is why I'm really interested in developing new programming models, but also new formal foundations to program and reason about these systems. And later in my talk, I'm going to talk a bit about what I've done in this space and some future ideas that I have. Thanks.
Hi, I'm Judith. I'm from the University of Auckland, and I'll try to take a simple approach to describe my research. So imagine building a house. So if you don't build the foundation of the house properly, the walls start collapsing. And then if you want to, you might do quick fixes to fix the wall, and then you might take shortcuts developing the house. And then if you want to add a new window to the house, it would be difficult to add a new window when the walls are not built properly. So this is similar in software development. If you don't take the proper path, the optimal path to software development, if you instead do quick fixes and take shortcuts, you might gain a short-term benefit delivering your product to the market early on to gain competitive advantage. But in the long run, the software quality degrades, and then this becomes difficult to add new features to the software in the end. So this phenomenon is called technical debt. And when it comes to technical debt, it needs to be managed to be able to have a sustainable software. So my research is looking at how to quantify technical debt, because that helps answering questions such as, is it okay to keep on taking on TD? Or should we stop now and refactor? So to make such informed decisions. And you'll hear more about my talk just after the coffee break in the at 3:30. Thank you.
Hello everyone, I'm Darishka Chasuri. I'm also from the University of Auckland. So my research is related to software dependency. So I think all of you here have used libraries when doing programming languages. So as your programs also like adding new functionality to your code, libraries also evolve separately. So this particular version that you're using now might be different when you look at the library maybe 2 months or 1 year ahead of you. So how can we and the functionalities that you have used from this library may also evolve. So how can we look at updating our software version? So it's not only sometimes the version number change, it can also be changes that the methods that you have also have evolved. And sometimes it's not only the method domain that you're looking at, it can be the function or the logical programming that happens inside the program that evolves. So there are certain characteristics that we are looking at to categorize these changes that happen in libraries. And is there a possibility to automate or guide the users that uses these libraries so that it will help in updating these dependencies? So that's my research, and I'll see you around 4 if you want to hear more about what I'm doing.
Okay, hi everybody. I'm Michael from Vienna, and in my research I want to infer grammars for ad hoc parsers. So basically, anytime that you transform a string, that you use, substring or split or trim or any of these string operations, you're actually parsing a string, right? You're imposing some kind of structure on the string, and that means you're also imposing some kind of grammar on the string. And I want to infer those grammars just based on the operations that you do on these strings. And if you can do that, if you can infer those grammars, then you can do a lot of cool stuff, right? You can show them to the user, but you can also generate, testing tools, for example. You can use this for fuzzing and many other applications that I will talk about. And the way I want to infer those grammars is to use an intermediate representation that has a refinement type system, where you can then infer a refinement type that includes constraints over these strings in your program. And those constraints, they're a bit unwieldy. They include linear arithmetic and universal quantifiers and so on, so we need to simplify them somehow. We need to minimize them into string predicates that very closely match, what a grammar looks like. And I'm gonna, tell you all about that in my talk later today.
Good morning, everyone. I'm Pankaj. I'm a PhD student at IIT Kanpur. So probably I'm the last guy, so we'll get to the coffee later. So what will happen? So I'll talk about synthesis, program synthesis. So now we have seen that recently program synthesis has been a very big success. Lots of tools like Sketch, Rosette, etc. We try to given a specification and set of programs in terms of language, try to find, choose a program which satisfies the specification. Now if you see these tools, what they actually try to synthesize a regular program. What we say regular means is that It's a sequential, imperative sequence of programs, straight lines of code. Now, what I am trying to show in my talk is that can we use this technique for programs which are beyond regular? Now, what do I mean beyond regular? Like, if you consider the concurrency constructs, like atomic sequences. In my last talk, we talked about parsers, synthesizing the parsers. They are not directly imperative programs. And the last one of another talk on this is about synthesizing this automated abstract interpreters engine. So we'll see more on this in my last talk. And I think my name is Lars, so we all know dessert is for the last. So thank you.